Welcome back. Let us go back to the script that we wrote in the last lecture for solving the Kohn-Hilliard equation and calculating the interfacial energy. So, I am going to take the same script and I am going to run it in Octave, and from there we will take up comparing it with the analytical solution that we have derived right now. Okay. So, as usual we go to Octave. So, I am in the right directory, and the code that we wrote was called interfacial free energy dot Kohn-Hilliard dot OCT. So, let us run that, and let me also show you that so the kappa value and A value that I am using are 1, that is for which I am trying to get the solution, and there is a small difference between the analytical solution that we obtained and the numerical solution that we are obtaining. See, the analytical solution was obtained assuming that as x goes to infinity, the composition remains at 0, as x goes to plus infinity, the composition remains at 1. However, when we are solving it numerically, because we are using Fourier transform, we have to use periodic boundary conditions. So, the other boundary condition that this remains at 0, that remains at 1 is possible if you use the finite difference technique, but as you will see later in 2D finite difference becomes too problematic. So, we want to solve it using Fourier transform. Fourier transform demands that you have periodic boundary condition. So, to be consistent with this periodic boundary condition is why we have made two interfaces, right. That is the reason why we actually calculated the interfacial energy and we divided it by 2, because instead of looking at one interface, in this case we are actually looking at two interfaces. Okay. Now, the solution for the Kohn-Hilliard equation analytically was obtained assuming that at x equal to 0 is where the composition profile is 0.5. So, if I want to superimpose the analytical solution on this curve, I need to know exactly where this is becoming 0.5. Okay. So, to do that, let me look at this. So, I am just focusing on the area. So, where it becomes 0.5, approximately 32.50. Somewhere around 32.50, I can see that this is becoming 0.5. So, what I am going to do is that I am going to, so let me get back to the figure, let me make it go to the full form. Okay. Now, I am going to take the Octave window. Remember, the solution that we obtained is here. So, it is C is equal to 1 by 1 plus e power minus beta x, where beta was A by kappa. Okay. A and kappa is 1. So, beta is 1 in our case. So, 1 by 1 plus e power minus x is what we want. So, x let us take runs from 0 to 64. Okay. So, the analytical solution that I want to plot. So, I want to say hold on. So, on the same plot I want to plot x comma 1 by 1 plus exponential minus beta is 1 x, but x should be shifted to have its origin at 32.50. So, x minus 32.50. So, that is the curve, and I think there is one. Okay. And I am going to plot it with red open circles, so that we will be able to easily identify that on the curve. So, let us go back to the curve and see what has happened. So, as you can see, the solution matches perfectly. Okay. Okay, the points are too close. Let me clear the figure. Let me run the code once more. So, this time let us plot only few points, so that we will be able to clearly see the interface. Okay. And so, I want to take, but I do not want to take so many points. Let me take once every 2 points, and I plot this, and let us go. So, you can see that the numerical solution is the line, the analytical solution is the points, and you can see that we are actually matching numerically the analytical solution. Okay. Now, because beta is A by kappa and that is 1, the interfacial energy which is gamma by 3, and the gamma was root kappa A, and so that is 1. So, you get 1 by 3. But the moment you change that, for example, let us go and make kappa to be 4, right. What should happen to, if I make kappa to be 4, the beta should become half. That means, the interface should become much wider and the interfacial energy should become twice. So, let us see if that is so. Okay. So, we run this. And now, the beta is half of the earlier beta. So, when we compare with the analytical solution, I now need to change it. So, let me go, I define x. Now, the solution, so beta is half of what it was. So, it should be 0.5 into this. Okay. So, now let us go and see. So, you can see analytically the solution is matching, and you can also see that the interfacial free energy has become double. We can go back and make A to be 4 and kappa to be 1. Okay. And again run the code. Okay. And in this case now beta is twice. So, the solution will match if I take 1 by e power minus 2 x, and the something went wrong. Okay. Probably the discretization I have done is not sufficient to take such huge A. So, let me take A to be 2 and see if, in which case it should be root 2. Okay. Yes. So, let us see square root of 2 into 1 by 3. Okay. So, that is the 0.471. So, that is the answer we are getting. So, it is scaling as root A, the interfacial energy, and to get the plot. So, we will take x and we now have to change this 0.5 to square root of 2. So, that is 1.4 whatever. So, now when we go see, again we will see the match. The reason why for 4 it was not running is that interface now you can see has hardly, let us look at that also. So, that is why it was giving NaN. See, interface now has 1, 2, 3, 4 points. Okay. When you make the A value still higher, there will be hardly any points at the interface, and hence numerically the dc by dx that you calculate blows up, and that is the reason why we had NaN. So, when you make A larger, probably you have to decrease the discretization distance. Okay. So, instead of taking dx to be 1, probably you have to take dx to be 0.5 or something, so that you will have more points to capture the interface. So, that the much sharper variations can be captured, then you will not have a problem. Okay. So, this is just to prove that the numerical solution that we obtained, at least in 1D, we are able to compare with the analytical solution that we are able to derive. Not just the solution, we are able to compare the interfacial energies, we know that they match, we know that the interfacial widths also match, because the profile is changing with the different alpha, the beta values, and but that we already know from the parameters that we use, and we are able to match. So, this shows that the numerical solution that we got is indeed correct. It also shows something else, that if you look at the error 0.471, the error in the energy that we are calculating is in the 4th decimal place. Okay. It is very hard to get this accuracy if you use a technique like finite difference, for example. Okay. It is very difficult to get to the interface profile which equilibrates and matches with analytical solution, because that will take much longer time and much computer resources for you to do. But even after you do, the error would still be higher than what we are getting. This is because spectral techniques are probably the best techniques for obtaining these numerical solutions. Okay. They are the most accurate that you can think of. So, that is the reason why we are getting very good accuracy for the interfacial energy also. We saw that even in the case when we had the interfacial energy to be 1/3, you can see that 1, 2, 3, 4, 5 up to 5 decimal places, I do not see any difference. So, it is 0.3333. So, that is 1/3 case. So, the solution is, and when we made it twice, we got 0.6666. So, 0.6666. So, it is very accurate solution that we are able to manage with the spectral technique. So, that is another thing that I wanted to draw your attention to. So, in the next lecture, we will look at another phase field equation, which is known as Allen-Kahn equation. Unlike the classical Kahn-Hilliard equation, I am not going to spend too much of time in deriving it. We will do a short derivation, and then we will try to solve it numerically, and you will see that that equation also has a tan hyperbolic kind of solution. So, that is what we will do in the next lecture. Thank you.